All right, so we are in this book here, Causal Inference and Statistics, Chapter 1, and we are on question 1.35, which is the famous Monty Hall problem. So I'll describe what that is here in a second, but our task here is to prove with Bayes' theorem that switching doors improves your chances of winning the car in the Monty Hall problem. Okay, but first you need to know what the Monty Hall problem is. So I've just pasted the description given in the book, and I will just read it here verbatim. So you're a contestant on a game show, and that game show is hosted by a man named Monty Hall. So Monty shows you 3 doors, A, B, and C. Behind one of them is a new car, and presumably that's what you, by picking the correct door, you get the car and you want the car. The other 2 doors have behind them an undesirable prize, which is goats. So if you guess correctly, you get the car, right? So if you guess that the car, if you guess correctly, if your guess aligns with where the car is, you get the car. Otherwise, you get a goat. Okay, so you guess A, and then Monty, who cannot show you where the car is, right? So importantly, Monty knows where the car is, and then he reveals the contents of door C. So you've picked A, and Monty shows you door C. And importantly, he cannot show you where the car is, okay? And so there's a goat behind it. And now he gives you the option of switching from door A to door B, okay? Or you can stick with A. So, and then whatever you get on this next guess is what you get, okay? So should you switch doors? Okay, so so generally the reasoning goes something like it won't matter if you switch doors because he's eliminated one of them. He's eliminated door C, and so now there's 2 doors, and if you split the probability evenly behind the 2 doors, A and B, then there's a 50% chance. So it doesn't really matter if you switch. But that's not entirely correct. Okay, the important thing to understand here is that you're actually given 2 pieces of information, and we're trying to extract as much information as you can. So at first, you know that there's a 1/3 chance that you've correctly picked and a 2/3 chance that you've incorrectly picked, okay? So your prior probability on having correctly picked is 1/3, okay? Now you're given some evidence, and that is what Monty Hall reveals. He reveals the contents of door C, okay? But importantly, what Monty has revealed is contingent on where the car actually is. And so his pick or his revelation reveals some amount of information about where the car actually is, okay, above and beyond just kind of the 50% threshold that we initially reasoned to with our guts, okay? So it kind of goes like this, okay? So on the times that you pick correctly, which is 1/3 of the time, he can show you either door. He can show you B or C. Doesn't matter. Okay? Because neither B or C actually has the car. You've already picked the door of the car. Okay? So 1/3 of the time, he offers you the choice of switching, and in these times, you should never switch, right? Because you already have the correct guess. Okay? But 2/3 of the time, you're incorrect, right? So now of those 2/3 of the time, he has to reveal the door without a car. So that means that in these times, 2/3 of the time, you should always switch, right? Because, because he's revealing the door that definitely does not have the car, and you have picked incorrectly, right? So you should always switch on those times, on the times that you have not initially correctly guessed. Now, of course, you don't know if you've correctly guessed or not. And that's why we're dealing with probabilities. So anyway, so since you're more likely to pick incorrectly at first, 2/3 of the time, then you should repick, right? So you should switch your guess 100% of the time, because most of the time you've initially guessed wrong. And of the times that you've initially guessed wrong, you should always switch, okay? So if we want to do this in Bayes' theorem, this is kind of how it looks like. It's not the prettiest thing in the world, so I'll kind of walk through it, but you can go through the math on your own. So what we want to show is that the probability that the car is in door A, given that you've picked A and he's revealed C, that this probability is less than the probability of the car being in B, given that you've picked A and he's revealed C. Okay, so we can just expand these posterior. So we can just expand both of these. These are posterior distributions, so we can just expand them into Bayes. Okay, and this is what Bayes looks like for the two expressions. Well, actually, for the first one. Okay, and then we just take 1 minus the probability that he would reveal. Well, we would just take 1 minus the car being in A, given that we've picked A and it's in C. Okay, and then we just run through and we get this value right here. So we get that the probability that the car is in A, given that we've picked A and he's revealed C, is 1/3, and then 2/3 of the time it's the other way around, right? And so obviously 2/3 is bigger than 1/3, and so we should always switch. That's what the moral of the story is there. Okay, and then this part right here just expands the denominator, and so you can go through that for yourself. So okay, that's it.